Okay, hi there, Calculus 3 students. This is Mr. Lewitt. We're going to do another video. Um, Hold on one second. Let me just make sure that's okay. Okay. I know I promised another video on the Chapter 11 homework, and I may still get to that, but I actually really want to start Chapter 12. I think it's very important because we are lagging behind a little bit. Um, you know, we only have until December 15th to cover four very big chapters, and it's already the middle of October, and I'm worried that we're not going to finish all four chapters. We can try. We can try. I have this bad feeling that we're only going to finish three of the four chapters, and maybe just start the fourth chapter a little bit, but we'll do as much as we can do, you know, with the time that we have. Okay, so I'm looking at your Chapter 12 homework, Part 1. It's 110 problems. I know I said I would try to limit it to 100 problems, but I think some of these problems are extremely important and you really should know how to do them. Okay, my goal is to work through the first 10 problems, and then I would like to show you problem 48, and I would like to show you an interesting Mathematica approach to solving problem number 48. Hopefully this video will not get too long, but we'll see. We have a lot to cover. Okay, so problem number one, or question number one. Give two pieces of information which taken together uniquely determine a plane. So the answer is going to be a point and a normal vector. The normal vector is a vector, any vector that's perpendicular to the plane. Now, answer D is almost right. It's any 3 points, but they have to be non-collinear points. Collinear points are points that belong to the same line. So I would have to, D would be correct if I modified this statement any 3 points that are non-collinear or not collinear, okay? So the answer should really be C. In this case, for this particular question, the answer is C, 1 point and a normal vector. Okay, excuse me, and that is correct. Next question. Where does the plane negative 2x plus 3y minus 4z is equal to negative 12 intersect the coordinate axes? Okay, so this is going to intersect the x-axis when y is 0 and z is 0. And then we're left with negative 2x is equal to negative 12, so x is going to have to be 6. Okay. The plane intersects the y-axis at the point, well, here I know x is going to be 0 and z is going to be 0 and y is going to be negative 4 because 3 times negative 4 is negative 12. Okay, and that's correct. The plane intersects the z-axis at x is going to be 0, y has to be 0, and then we're left with negative 4 times z is equal to negative 12, so then z is going to have to be negative 3. Let's see if that's correct. Oh. Okay, what happened? I think I made a mistake here. Oh, I'm sorry, that should be positive 3, not negative 3. Right, because negative 4 times 3 is negative 12. Sorry about that. Okay. Let's move on to the next question. What is an equation of the plane with a normal vector 1, negative 1, 1 that passes through the point 0, 1, 0? Okay, so this is going to be really easy. So I have a normal vector. N is equal to 1, negative 1, 1. This is the normal vector for question number 3. Okay. And if I take the dot product of my normal vector, and let's see, the point is going to be, okay, 0, 1, 0. So the point should be x minus 0, which is just x, okay? And then y minus 1, and then z minus 0, which is just z. And remember, that's going to be equal to 0 because, okay, remember the dot product of two orthogonal vectors has to be 0. So x, y minus 1, z, okay, that's going to be any vector in the plane, okay, whose, any vector in the plane whose tail is going to be at this point. So we know that the dot product of those two vectors has to be 0. So I could expand this entire expression, expand, shift enter. Okay, so I'm going to have x minus y plus z is equal to -1. X minus y plus z is equal to -1. Okay, and that is correct. All I did was I put the +1 here on the other side of the equal sign, so it's -1. Okay, not a big deal. It's basic high school algebra, right? Okay, number 5. To which coordinate axes are the following cylinders in R3 parallel? R3 is three-dimensional space. You would know that if you're reading your textbook. You guys have to read the textbook. I'm really concerned that some of you are not reading the textbook. Please read the textbook. Okay, my videos are not a substitute for the textbook. My videos are only designed to supplement the textbook. Okay. To which coordinate axis is the cylinder z squared plus 2y squared equal to 8 in R3 parallel? Well, that's going to be easy because I don't see an x here, so I know that this is going to be parallel to the x-axis. Very simple. To which coordinate axis is the cylinder x squared plus 2z squared is equal to 8? In R3 parallel, well, I see an x and I see a z, I don't see a y, so this is going to be parallel to the y-axis. To which coordinate axis is the cylinder x squared plus 2y squared is equal to 8 in R3 parallel? This is parallel to the z-axis, and that's correct. What are the traces of a surface? Okay, hold on. Let me expand the window a little bit. What are the traces of a surface? Let's see, choose the correct answer below. The intersection of the surface with a plane parallel to one of the coordinate planes. Should be B. Okay. Number 6. Find an equation of the plane that passes through the point -2, 2, 0 with a normal vector -1, 3, -3. Okay, again, this should be pretty simple. Okay, so my normal, let's define a new normal vector. My normal vector is going to be, whoops, -1, 3, -3, -1, 3, -3. The normal vector for question number 6. Question number 6. Okay. And the point is negative 2, x is negative 2, y is 2, z is 0. Okay, pretty simple. So normal vector x minus a negative 2, right? And that's just going to be x plus 2. Y minus 2, and then z minus 0, which is z. And the whole thing is equal to 0. And why don't we just expand it? Expand. Okay, so it looks like I have negative x plus 3y minus 3z is equal to positive 8. So negative x plus 3y minus 3z is equal to positive 8. I'm just taking the negative 8 and I'm moving it to the right side of the equal sign. And that should be correct. Okay, so far really nothing here is too complicated, right? I mean, some of the homework problems are difficult, but some of them are super easy, and you should be able to get them done like in a minute or 2 minutes. So I understand it's a lot of homework, but I feel that, it's really not as bad as you think it is, because there are some really easy problems here that you should be able to solve very quickly. Granted, some of the problems are very challenging, but a lot of them are not like that. Okay, number 7. Find an equation of the plane that passes through the point. Okay, this is like number 6, guys. This is really very similar. It's really the same thing as 6. So why don't we move on? Let's move on to number 8. Okay, this one's a little different. Find the equation of the plane that is parallel to the vectors 2, 0, 1 and 0, 3, 2, passing through the point 3, 0, negative 2. Okay, let me think about this for a moment. Find the equation of the plane that is parallel to the vectors 2, 0, 1 and 0, 3, 2. Excuse me. Okay, so if the plane is parallel to these vectors, now think about it. If the plane is parallel to these vectors, that means that the normal vector of the plane is going to be orthogonal to these two vectors, which means I need to find the cross product of these two vectors. Okay, so that should be easy. So normal vector is going to be the cross product of 2, 0, 1 and 0, 3, 2. Okay. So this vector is going to be orthogonal to these two vectors here. Okay, so I'm looking for a plane that is parallel to these two vectors, which means the normal vector of the plane is going to be orthogonal to the plane, but also orthogonal to these two vectors. And then dot product of n, x minus 3, y minus 0, and z, z minus a negative 2, or z plus 2, is equal to 0. Excuse me, I have a sore throat this morning. Sorry about that. Expand. Okay, so we have negative 3x minus 4y plus 6z is equal to negative 21. I'm not sure if Pearson will accept this because of the negative. So we have negative 3x minus 4y plus 6z is equal to negative 21. So I'm just moving I'm moving the positive 21 to the right side of the equal sign, where it's going to change to a negative 21. But I have a feeling Pearson wasn't going to like this. Oh, okay. Okay, so I stand corrected. Pearson, I've noticed a lot of times, Pearson wants the number on the right side to be positive, which is not a big deal. Then you just multiply the entire equation by a negative 1, and then you would have 3x plus 4y minus 6z is equal to positive 21, which is really the same thing. Okay, that's the same thing. Number 9. Find the equation for the plane through the points. Okay, here we have 3 points. So I'm going to define a matrix. I have x minus 4. I have y minus 3, z minus a negative 4, which is z plus 4. I have x minus 1, y plus 2, z minus 5. And then I have x minus a minus 4, which is x plus 4, y and z, y minus 0, z minus 0. Okay, so this is what my matrix looks like. Now, x, y, and z, those are any points in the plane. As long as x, y, and z are members of that plane, as long as x, y, and z belong to that plane, then I know that the determinant of this matrix is going to have to be equal to 0. Okay? So the determinant of my matrix must be equal to 0. And why don't we just expand this? Okay, so now I have 7x minus 60y minus 31z is equal to negative 28. I have 7x minus 60y minus 31z is equal to negative 28. And that's correct. Okay, this is really the same thing. This is, although we can solve this one a little bit differently. This is the same type of question, but we can solve this differently, and we'll still arrive at the same answer. Find the equation for the plane through these 3 points. Okay, so I have P0 is equal to 3, 3, 4. I have Q0 is equal to negative 1, negative 2, 2. And I have R0 is 4, 3, 3. R0 is 4, 3, 3. So this time I'm going to take the cross product of 2 of these vectors. Okay, cross product of 2 of the vectors. And then the dot product of this cross product with the 3rd vector. So the dot product of the cross with R0 is equal to 0. Let's expand it. Oh, you know what? Here, hold on. There we go. Okay, so something is not quite right here. why am I getting, oh, I see what the problem is. Now I see, okay. Silly me. So this is going to have to be x minus 4. I'm looking at the R0 vector. Y minus 3, z minus 3. Okay, where x, y, and z, those are the three elements of a point in the plane. Okay, that makes a lot more sense. Okay, so I have 14x minus 10y minus 3z is equal to 17. Okay, and let's see if I could simplify that. Well, yeah, you get the idea. Okay, Mathematica is being stubborn, but all I'm going to do is place the negative 17 on the right-hand side of the equal sign where it becomes a positive 17. So the answer is 14x minus 10y minus 3z is equal to a positive 17. Okay, so Pearson's complaining. Oh, I see what I did. Okay. Use the vectors PQ and PR to find the, okay, I see what I did wrong. So, okay, so I'm gonna have to find, okay, I'm glad I'm working on this problem. See, teachers make mistakes too. These are my 3 points. These are my 3 points. Okay. These are points. They're not really vectors. They're not really vectors. So PQ is going to be P0 minus Q0. Okay. And then PR, well, actually, technically, it really doesn't make a difference for this problem, but technically this would be Q0 minus P0. You know, but technically for this problem, it's not a big deal. It doesn't really matter. PR is going to be R0 minus P0. Okay, so now I have vectors. Clear cross, because I'm going to use that variable for something else. I'll redefine it. PQ, PR. Okay. Dot product of cross, let's see, PQ, PR, x minus 1. Oh, I'm sorry. Let me look at the original point here, R0. Okay. I'm looking at R0 right over here, guys. I'm looking at R0. So it's going to be x minus 4, y minus 3, z minus 3. And let's expand that last answer. 5x minus 6y plus 5z is equal to 17. 5x minus 6y plus 5z, okay, 5x minus 6y plus 5z is equal to 17. Okay, so my mistake originally was treating these points as vectors. So that wasn't a good idea. So what I needed to do to create my vectors, okay, let's see. To create the vectors, I had to take the difference between 2 points. So PQ is Q0 minus P0. PR is R0 minus P0. Then I take the cross product of those 2 vectors, and I dot that with one of the points, and that will give me, and of course I set it equal to 0, and then that's going to give me the equation of my plane. Okay? And there actually is a way that you can check. There is a way that you can check. So f of x, y, z is equal to 5 times x minus 6 times y plus 5 times z. Okay, so let's try it. P0 f of 3, 3, 4 is 17. Q0 f of negative 1, negative 2, 2, still 17. And R0 f of 4, 3, 3 is still 17. So I know that I have the right answer. That's a way of checking your work to see if you have the right answer. Okay, let's take a look at, I believe the problem I looked at last night was 48, which was a little tricky, and I thought it was really interesting. Oops. Find the point or points at which the following plane and curve intersect. So the plane is 3x plus 4y minus 8z is equal to 0. The curve is r of t is equal to 2 cosine t, 2 sine t, and cosine t, where t is defined on the interval from 0 to 2 pi. Okay, so first of all, what we have to do is define r of t, which is a vector valued function, and that's going to be 2 times cosine t, 2 times sine t, and then cosine t. Okay? And then we have this plane here, 3x plus 4y minus 8z is equal to 0. Okay? So in this equation here, 3x, x refers to the first member of the vector valued function. Y refers to the second member of the vector valued function. And z, z refers to the third member of the vector valued function. So if I have a vector or a list in Mathematica, I could do something like this. Oops, sorry about that. This refers to the x element or the first element of the triple, right? This refers to the second member or the second element or the y element of the triple. This refers to the z element or the third element of my triple. I hope everyone can see that. So the equation that I end up with is going to be 3 times r of t, 1, which is really 3x, plus 4 times r of t, 2, which is really y, minus 8 r of t, 3, which that's the z element. So 3, 4, and negative 8, and it's equal to 0. So I end up with this equation, negative 2 cosine t plus 8 sine t is equal to 0. And I have to solve this equation. So for some t which is between 0 and 2 pi, okay, I know that negative 2 cosine t plus 8 sine t, or 8 sine t minus 2 cosine t, same thing, is equal to 0. So some of these trig equations can be really tricky to solve. Some of them can be a little bit difficult to solve. So what I recommend in this case is using Newton's method. Newton's method is this wonderful, hold on one second, I just want to take a look at their answers. Okay, so Newton's method is a wonderful method for finding an approximate solution to a pretty complicated equation. And we can define our own Newton's method function in Mathematica. Now, just a couple of things that we have to go over here, okay? Mathematica can figure out derivatives. So what is the derivative of 10x squared with respect to x? It's 20x. Now, what if x is equal to 2? I would expect the answer to be 20 times 2, which is 40, right? But that doesn't work because 2 is not a symbolic value. So what I would have to do is something like this, where x is equal to 2. What is the derivative of 10x squared with respect to x? And then replace x with 2. So 20 times x and then 20 times 2 is 40. Okay? Also, when you're defining functions in Mathematica, you can define what are called local variables. For example, f of x and y. Okay, f of x and y module z is equal to x plus y. Or we could do something like this. How about a is equal to x plus y, b is equal to x minus y, and then a times b. So let's see, 5 and 4. So is that true? 5 plus 4 times 5 minus 4, that's equal to 9. So a and b are local variables inside my function definition. A is equal to x plus y, b is equal to x minus y, and then I just multiply the two values, a times b. Okay, let's try it again. F of 17 and 12. It's 145. Is that true? 17 plus 12 times 17 minus 12, that's 145. So you can use module to declare local variables, which is very convenient. Okay, so let's try this. Newton's method. Now remember, this is a Calculus 1 formula. Remember how it worked? Newton's method, so we're going to have a function. Here, I'm going to clear f. Okay, we're going to have a function. We're going to have a guess. And the number of iterations, if the number of iterations is 0, just give me back my guess. Shift Enter. Newton's method. Now, what if the number of guesses is greater than 0? This is the condition. This symbol right here means the condition is that n is greater than 0. Okay. Then I'm going to have a module. Okay. The derivative, I'll call it deriv, is the derivative of f of x. I'm going to use y. I cannot use x. I'm using x already. So I'm going to use a different variable. I'm going to use y. And then y, we substitute x for y. And then I have another module. My new x is equal to my old x minus f of x, okay, divided by deriv. This is deriv right over here. It's the derivative of f of y with respect to y, but then y is replaced with the actual number x. X is a number. And finally, I have Newton's method, f nu x n minus 1. Shift enter. Okay, so let's see if this is going to work. Let's do something simple. Let's choose a simple function. Okay. Newton's method. What about the parabola 100 minus x squared? Now, instead of using x as my variable, I'm just going to use any generic variable. I could use the hash symbol. The hash symbol is like a generic variable. 100 times the variable squared. And wherever I see a hash in Mathematica, I must conclude with an ampersand. Okay. My initial guess can be 20. And I'll use 100 repetitions. Shift enter. Okay, this is still, okay, what is the problem here? Okay, abort evaluation. So something, oh, you know what? Okay. I'm going to rewrite this. Instead of using exact numbers, let me use floating point numbers. I'm going to use floating point numbers instead of exact numbers, and let's see if this works. Let's see. Shift enter. Yeah, it does work. So the problem is that I was using exact numbers, and in fact, we could probably modify this function so that it will use floating point numbers automatically. So let me see. Well, let me see here. We could simply, right over here, okay, so let me clear Newton's method and redefine it. Shift enter. And then here, I'm going to say for the derivative, let's multiply it by 1.0. By 1.0, and that should take care of the problem. Okay, why am I getting, oh, I see what's wrong here. Okay, we needed, okay, there we go. There we go. So let me erase this. So Newton's method, 100 minus some variable squared. I'm going to guess 20, and let's do 100 repetitions. That's fine. So we know that 100 minus 10 squared is equal to 0. So what I found was a root of the function using Newton's method. The problem with Newton's method is that it will only give you one potential root. There could be two. So for example, Newton's method, 100 minus some variable squared. How about negative 40? We'll do 100 repetitions. So this is the other root. 100 minus negative 10 squared, we know that it's equal to 0. So Newton's method is simply a way to find the root of an equation. And this is how you would define it in Mathematica. This is how you would define it in Mathematica, right here. Well, and also right here. It really requires two definitions, two function definitions. Okay? So for this particular problem, we need to find a root of negative 2 cosine t plus 8 sine t. So why don't we do that? Newton's method. Let's see. Well, actually, I have it stored in an equation. My equation is equal to this. I don't want to use the equals 0 part because this is automatically assumed by the algorithm. So equation is equal to equation. Give me the first part. So equation, okay. Newton's method equation. I know the answer has to be somewhere between 0 and 2 pi. Why don't we use pi, and let's use 100 repetitions. Shift enter. Okay, so okay, this is taking too long here, so let's abort evaluation. Okay, I think the problem here, the reason it's taking too long is because this needs to be a floating point number. Pi is not a floating point number. How can I change it into a floating point number? That's how I could change it into a floating point number. So let's do that. Let's do that. Newton's method, okay. And it's still taking a pretty long time. Oh, you know what I think? Okay, hold on one second. Again, let's abort the evaluation. Okay, so here, okay, so here what I'm going to do, instead of using equation, I'm going to use negative 2 cosine any variable plus 8 sine any variable, and that with an ampersand or hash. And let's see what I'm going to get. Shift enter. Okay, much better. That worked a lot better. So I'm getting 3.3865, 3.38657, etc., etc. Is that less than 2 pi? 2 times pi. Yeah, that's less than 2 pi. However, there could be another answer. There could be two answers. So this is one possible answer. I'll call it T1. That's T1. There could be another answer because 0 to 2 pi is a whole revolution. So there could be another answer. So Newton's method, negative 2 cosine some variable plus 8 sine some variable, pi over 4, and let's do 100 repetitions. So this time I'm starting out with a different guess, a smaller guess. And sure enough, there are two answers. There are actually two answers. So I have T1 and I have T2. Okay, now I'm going to have to look at the answers that they have. Now, the answer, I go back to my equation. What is R of T1? This is r of t1, and what is r of t2? So I can see here that there are two answers, and actually there's simply negatives of each other. Negative 1.94, positive 1.94, negative 0.48, positive 0.48, negative 0.97, positive 0.97. So let's go over here. I'm going to look at the first answer. What is 17 times the square root of 17 divided by? Well, I know there are two answers, so it can't possibly be A. It can't be E. Let's take a look at B. What is 8 over 17? Okay, that's not the right answer. What is C? Okay, right over here, I'm looking at C. What is 8 times the square root of 17 divided by 17? Yeah, that's 1.94, which is exactly what I have here. And then 2 times the square root of 17 divided by 17, which is 0.485, etc., etc. And then right over here, I have 4 times the square root of 17 divided by 17, which is the number that I have over here. So actually, guys, it's going to have to be B. I'm sorry, C. It's going to have to be C. So these numbers correlate perfectly with the floating point numbers that I have. And we can see all the numbers here are positive, all the numbers here are negative. So I know that C is going to have to be the answer. C is going to have to be the answer. Okay? So a problem like this can be a lot of work, but if you understand Newton's method and how to use it in Mathematica, it's really not that terrible. This is Newton's method. Copy it into your Mathematica notebook and please use it, because it can help you to solve some very difficult equations, all right? I mean, Newton's method is not perfect, but it's actually pretty useful. It's actually a very useful method, and it converges pretty quickly. For 100 repetitions, you should definitely find one of the roots of the equation, okay? But remember, you have to start out with an initial guess. You have to start out with some kind of a guess. So this is my guess here. This is my guess, and this is the number of times I apply the algorithm. This is the algorithm. Now, if this is a little bit too much for you, you can always use find root. Find root is another command or function in Mathematica. For example, 100 minus some variable squared, and we're going to start out with 12. Actually, let me use, okay, and here t is my variable, and my initial guess is 12. We know 100 minus 10 squared is equal to 0. Find root 100 minus t squared. This time we'll use a different initial guess. How about negative 15? So we know that 100 minus negative 10 squared is also equal to 0. So the roots of 100 minus t squared, that's going to be 10 and negative 10. Those are the two roots. You could use find root as well, but I think it's more fun and more challenging to build your own root finding functions in Mathematica. So this really does the same thing as find root. But for here, I strongly recommend that your function should be an anonymous function. An anonymous function uses these lambda variables. They're called lambda variables. So instead of using x, y, z, a, b, c, whatever, you simply use the generic hash symbol, and at the conclusion of your function, you use the ampersand. And this is called a lambda function. A lambda function, which is also called an anonymous function, because it doesn't really use a named variable such as x, y, z, x or y, or z, or a, or b, or c, or s, or t, etc., etc., etc. Okay? And this is called a lambda function or an anonymous function. So with Newton's method, I strongly recommend that this is what you use. If you decide that you want to use, if you decide that you want to use my Newton's method function, okay, I strongly recommend that your function should be a lambda function or an anonymous function. I think otherwise you may run into some problems, and this function may not work that well for you. Okay? All right, guys, this video is more than 50 minutes long. I think that's long enough, and we're going to stop right now. Have a great day and good luck with your homework. Goodbye.